Okay, so we've covered, I think, all of the content on differentiation, so now I'm just going to do a bunch of blitz questions and things like that until we've gotten to the point of mastery on taking derivatives. So that will be the first and third part. I also wanted to spend a little time on this summation notation, since you mentioned not having seen it before, since this is technically supposed to be an Algebra 2 topic. Like, you probably remember the Khan Academy video I sent you was from his Algebra 2 unit on sum notation, but I realized that in Jim Thorpe it's actually not usually covered in Algebra 2. So yeah, we can just spend some time on this to make sure it's clicked, because when we do integration, which is I think chapter 5, and then sequences and series, which I think is chapter 8, these will rely heavily on sum notation, so I want to make sure that you've seen it before we get there. So that is the plan. But first, the warm-ups. So I stole these warm-ups from the Calc 1 problem sets at MIT. So these are just actually these are exercises. The problem sets come in two parts. Part 1 is exercises, and part 2 is problems. So these are exercises which are easier, which is why they're very short. That's why I've made them warm-ups. But anyway, okay, so here's an exercise. If a is a constant, and we define this function f of x as x plus a over x squared plus 1, then what is the derivative f prime of x?
So I feel like we may have to start by breaking this into two separate functions, but it's x over x squared plus 1 plus a over x squared plus 1.
You can do that, yeah. You can either quotient rule directly without breaking it up, or you can break it up into two pieces and differentiate each one by linearity. That's fine. Okay. Good.
Now I had to remember the quotient rule.
Oh yeah.
This is what I have the consolidation document for.
I think it should be derivative of the top times the bottom left alone minus the derivative of the bottom times the top left alone all over bottom squared.
Yeah, it's a lot faster than waiting on overleaf to load.
Yeah.
So it's almost the product rule, except it's subtraction in over g squared.
Yeah, you can actually prove this using the product rule, right? You write this as f times 1 over g, and then you use the product rule and the chain rule, because this is g to the power minus 1, and g to the power minus 1 by the power rule gives you the minus sign. So, yeah, that's where as you say, it's just like the product rule except the minus.
Okay, so let's see. We have that in our first function where we have x over x squared plus 1. It is going to be deep thinking. It's going to be 1 over, excuse me, is going to be x squared plus 1 minus, begin left parenthesis c. Let's see. Oh wait, that is, wow, I'm not remembering things good today. This is going to be 2x, I believe.
Yeah, derivative of the bottom is 2x.
And it's just all over, oh wait, no, I forgot about f. That's going to be thinking x, yes.
Good. All over.
All over. Still thinking. What is x squared plus 1 squared? Let me think.
Oh, we don't have to FOIL it out. We'll just leave it like that.
Okay.
We're going to run out of room here, so let me just draw a divider for my eyes. Okay, then the second piece, which I'll write on the second line.
In deep thinking, I believe we were taking ddx of a. I'm trying to remember. We went over this a lot last time, of course.
Yeah, so a is a constant which doesn't depend on x, right?
Okay, so it's 0.
Good. So the first is 0, and then minus the other thing.
Two x times thinking. Yeah, 2x times a.
Good. That's still all over x squared plus 1 quantity squared. And then if we want to tidy this up a little bit, we could combine, because the same denominator. So this is x squared plus 1 minus, well, this thing is 2x squared, so we can combine like terms here. And then there's minus 2ax, I'll write that as, all over x squared plus 1 quantity squared. So at the end of the day, when you kill the two x squared terms, combine them, it should be minus x squared minus 2ax plus 1 over x squared plus 1 quantity squared. Good.
Was there a quicker way to do this?
Yeah, so instead of breaking them up, you could have just done the quotient rule on this thing, where you would let f be the function x plus a, and g be the function x squared plus 1. So then it would have been one step. It would have been f prime would have been 1 times g, which is x squared plus 1, minus g prime would have been 2x times f, which is the quantity x plus a. So then we wouldn't have had to combine fractions, but it's not that much faster. It just saves one step.
Okay.
Good. Okay. Here's the one-step way to do it. So yeah, if you did it that way, you would have had, as I say, derivative of top times the bottom minus derivative of the bottom times the top over the bottom squared. And as you see, that gives us the same thing we found by splitting it up. Good. Questions on this?
I have no questions.
All right, one more warm-up. All right, so you can think of this, so this will be useful when you do the daily challenge about kinematics. So you can think of this capital D as the Pythagorean theorem giving you the distance between 2 points, right? This is just the distance formula. So this gives you the distance between the points, say, x0 and a y0, right? Because by Pythagoras, you would take the square root of x minus a squared plus y0 minus 0 squared. So this is just the distance between 2 points, but we're not going to think of it, we're not going to use the geometrical interpretation. We're just going to take this as some God-given function which was handed down to us and evaluate the derivative. So we're going to pretend that, well, not pretend, we're going to assume all the other symbols besides capital D and X are constants. So A is a constant, Y0 is a constant, and in particular we know the derivatives of constants are 0. So if you assume these things, and then take the derivative of capital D with respect to x, then what do we get?
I totally missed what you were saying there, but I've been thinking about the chain rule here. Is that?
Yeah.
Okay.
Probably good.
Oh wait, yeah, it's in the title. Oh my god.
Sorry, that was too funny.
I didn't realize that until now. Okay, so our outer function is going to be x to the power of 0.5, and inner function is everything there except for the square root.
Yeah, good.
That's going to get very ugly, I think.
Yeah, it's not that bad. So what's the derivative of thing to the power 1/2, the outer function?
I'm trying to remember if we have shown the nx to the power of n minus 1 rule for real numbers.
Yeah, so remember in the logarithmic differentiation daily challenge, in the challenge where you take the log of a function, then take the derivative of that, we use the log thing to prove that ddx of x to the r, where r is any real number whatsoever, not just integers or fractions. This is always r x to the r minus 1. So we've actually proved this for all real numbers.
So I guess we have that the derivative of x to the power of 0.5 is 0.5 times x to the power of negative 0.5.
Good. So I don't like decimals. I'm always going to write things as fractions. So so as you say, it's 1/2 times the inside function to the power of minus 1/2, right? Negative 0.5. Okay.
Yes.
And then we multiply by derivative of the inside chunk. So what's that?
Deep thinking. Do we need to do we need to FOIL x minus a squared?
You can, but I'm very lazy, so I prefer to just apply the chain rule to this rather than FOIL it out, because it's faster.
That makes much more sense. So the addition of derivatives, we see that we can split this, and the chain rule, we have that for an outer function x squared and inner function x minus a. Let's see. We're going to have two 2 times 1 for our inside, I believe.
Good. And then don't forget the outer, or when you take the derivative of
Right.
the outside function, inside left alone, right?
Right.
Good. Okay, see, that's...
Oh, yeah.
What'd you say?
Should we have a left parenthesis there? So it's clear that we're adding this onto the y squared.
To the y squared.
Oh,
You mean like this, you want?
sure.
Yeah, sorry, this means the whole first line times the second line, but I don't know.
Well,
Good. Okay, so I agree. The derivative of the inside is twice x minus a plus 0, because the derivative of the y squared piece is 0, so that's actually all we need. And then we could rewrite this if you want, because the 1/2 cancels the 2, so we have an x minus a upstairs, and then just put negative exponents in the denominator, which is root x minus a squared plus y0 squared. But there's a nice thing that we could actually rewrite this using the definition of d, right? Because that thing in the denominator, square root of x minus a quantity squared plus y0 squared, is exactly this thing d that we started with. So if you prefer, we could rewrite this as x minus a over big D, which is, I think, a little cleaner. But okay, that's the second warm-up. Thoughts on this guy?
I have no thoughts.
Good. Okay, let's make sure that this actually agrees with what I did yesterday. So, yeah, chain rule, this is what we did. X minus a over this chunk, I think we agree, and indeed, that is the same as x minus a over d. Good, it's comforting when we don't make mistakes. Okay. Alright, hopefully you feel adequately warmed up. Okay, so now we can do the summation notation stuff. By the way, it was just so I have a sense of how fast I should go, so I'm not boring you. Did you read any of the summation references, or like watch any videos or something, so that you've already seen some of this, or not?
Summation references, question mark.
Yeah, so on Slack when you were doing the Leibniz stuff, and you said you hadn't seen summation notation, and then I sent some links to places.
Right. I did not get around to any of those, unfortunately. I am a lazy or forgetful. I don't know the difference.
That's fine. Okay, so then I will go slightly more slowly than I would have planned, so that's fine. Okay, so first let's define what does this symbol capital sigma mean. So, well, by the way, in case you didn't know, in LaTeX you do this with /sum, and it gives you a capital sigma. So this is the Greek letter which makes the same sound as S in English, so that's why we use it for sum. S for sum, capital sigma. So often in calculus, especially when we get to integrals and infinite series, much of later chapters is going to be devoted to asking the question, if you add up a lot of numbers or functions, infinitely many of them, does that sum of infinitely many terms converge to something in the sense of a limit? And of course we can't always write down infinitely many things added together, because we don't have infinitely much paper. So it's easier if we have a formula that allows us to express a sum by just telling you what each of the terms in that sum look like. So that's what's called summation notation, or sometimes sigma notation. So here's an example. Suppose we want to write this finite sum, and it's written 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5 plus 4 times 6. So the pattern is completely obvious. You take 4 times each positive integer between 1 and 6. So you might ask, is there an easier way to say, sum in Python, I guess you would say something like sum for n for, n in range between You would have to do 1 and 7 because of Python, but you see what I'm saying. Is there an easier way to write this that tells the reader, rather than having to look at this and guess the pattern, that it's 4 times each integer, that just makes it explicit, right? It's 4 times each integer from 1 to 7. And there is. What you do is write this sum, or capital sigma, and then you put a formula for each of the terms in the sum. So this is, like in the Python example, the thing inside the list comprehension. So 4 times n just means 4 times each of the integers. Which integers? Well, to figure out which integers you're summing, you look at the bottom and say we start at 1, and then we go up to and including 6. The last value of n is 6. So this is different from Python. In Python, you don't include the last one. In summation notation, you do. So this means write 4n going from n equals 1, the first one, here's n equals 1, up to the top value, n equals 6. So, and I've used this word, I think. I don't know, I probably should have defined this, but the dummy variable appearing in the sum is called the index, or sometimes the index of summation, if you want to make it very, very clear what you're talking about. So this is the idea. We write a formula for each term, tell you the lower bound, the upper bound, and that is a shorthand for this long sum. Good. Questions on this?
I have no questions.
Okay. Hopefully it's clear why this is an Algebra 2 topic, 'cause it's not rocket science. Okay. Let me be a little more general. So here's the general definition. So let x sub I, you read this x sub I, be any expression which depends on an integer. So in the previous example, we would have said x sub I is 4 times I, right? I wrote it as 4 times n on the previous slide, but it's a dummy variable. We can call it whatever we want. So if x sub I is any expression which tells you what a term in the sum looks like, and it depends on the integer I, where we call I the index now, and we pick 2 bounds, a lower bound, which I'm now calling lowercase n, and an upper bound, which I'm now calling lowercase m. They're 2 integers. Then here's the general definition of summation notation. So the sum of x sub I, starting from I equals n, and ending at I equals m, is defined, maybe I should use 3 lines, because this is a definition. It's defined as this sum, x sub n, the lower bound, n plus 1, n plus 2, dot dot dot, m minus 1 up to m. So you just add up all of the terms, plugging in each value starting from n and going up to n. And just to emphasize again that here I is a dummy variable. So very often you will relabel the index in problems using summation notations. You change I to some other letter, and as you pointed out on Slack, letters that make you think of integers include like I, j, k, n, and m. So they're common choices. Okay. Just being very explicit here. Thoughts on this?
I do not have any thoughts.
Good. Alright, so here's a challenge for you then. So if we're writing the sum from k equals 3 to 7 of 2 to the k, and I ask you to write out all of the terms explicitly, or at least tell me which terms to write out explicitly, what are the terms I should put on the right side?
I believe what should appear is... Alright, this is... I was about to ask a stupid question.
What was the stupid question?
I was gonna ask if the sum was multiplication.
Oh no.
Yeah, that would have been bad. Okay, we have 2 to the power 3 plus 2 to the power 4 plus 2 to the power 5 plus 2 to the power 6 plus 2 to the power 7.
You started tripping over the words at the end of that. Good. Yes, that's right. So, I mean, surely you have memorized all of these numbers because they appear in file systems and computer nerds. So, yeah, so these are these things. And I don't feel like actually adding these up, but I do it on the next slide. So, yes, this is what we mean by this. Plugging in from 3 to 7, and then adding up all of the terms. And indeed, I think it's 248 if I remember correctly. But if you add 8, 16, 32, 64, 128, it's 248. Good. Nothing super challenging, but I just want to prove a couple of things, because these are often used, for instance, in the Leibniz stuff, where you break up a sum into 2 sums. So, I mean, again, this is kind of an obvious proposition, but we have to prove it. So, proposition, if x sub I and y sub I are two indexed expressions, so these are two expressions that depend on the index I, and we sum from n up to m, so those are two integers, then my claim that I will prove is that the sum from I equals n to m of x sub I plus y sub I is the same as first taking the sum from I equals n to m of x sub I, and then adding that result to the sum I equals n to m of y sub I. Why is that true? Well, hopefully it's almost painfully obvious. You can add things in whatever order you like. Addition is commutative. So if you start with the left side and expand out this sum just using the definition on the previous slide, right? So the definition just means add up all of the things from the lower index, the lower bound to the upper bound. If you do that, adding up all of those, we start at n, so xn plus yn plus xn plus 1 plus yn plus 1, blah, 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 up to xm minus 1, ym minus 1, xm, ym. So that's the definition of the sum. Then I just kind of reorder these, because I'm allowed to sum these in whatever order I want. So I move all of the x's over here, and put those into the x sum, so here's the x sum, and move the y's over here, put them in a y sum. And then by the definition of summation notation, this is precisely the sum from I equals n to m of x sub I, and this is precisely the sum from I equals n to m of y sub I. So, as we would expect, sums work. You can sum them in whatever order you like. This seems obvious, but let me just stress that this is obvious for finite sums. If you're summing up finitely many terms, you can sum them in whatever order you like. As we will see if we go up to chapter 8, if you are summing infinitely many terms, I equals 1 to infinity of x sub I, where I have to define what this means. I haven't told you what it means to add up infinitely many things, but this is not commutative. This is very strange. If you're adding infinitely many things and you change the order in which you are adding them, you can get a different answer. This is very surprising. This is one of the great achievements of calculus, I think, is to show why this is true and tell you under what conditions you are allowed to commute terms in an infinite sum without changing the answer. So, again, it seems obvious, and it is obvious in the finite case, but I just want to stress that we shouldn't get too cavalier about this and assume that it works in lots of other cases. But anyway, okay. Questions here?
So how far off are we from proving the thing to the right?
This thing? Let's see. So we're almost done with chapter 3. Then chapter 4 is applications of derivatives. 5, I think, is integrals. 6 in AOPS is this weird thing about exploring infinity, which I think is a little strange. Then, if I remember correctly, I think 7, chapter 7, it's either 7 or 8, I want to say 7, is sequences. So this chapter 7 is where we will prove this thing, that the sum is not commutative. Assuming you want to continue after chapter 7. I mean, in a high school calculus course, you would either take calculus AB or calculus BC, and AB roughly covers in AOPS chapters 1 to 5, and the BC course goes faster. That covers chapters 1 to 9. So, I mean, it depends on what you want to do. If we get to the end of chapter 5 on integrals and you say, all right, I've had enough of this shit, I want to stop doing this, then we can stop there. But if you want to continue and finish the book, then when we get to 7, we will prove this statement, that adding up infinitely many things does not commute.
I'd want to get up to 7 just to see how this is true.
Yeah, it's very mysterious. This is kind of a mind-blown moment for me when I saw that. Good. If you like, when we get to that chapter, we can also see one of the most mysterious expressions which is commonly written in string theory books, which is the following. Sum from I equals 1 to infinity of I. What does that mean? Well, you add up just the integer itself from 1 to infinity. 1 plus 2 plus 3 plus 4 plus dot dot dot. So obviously this sum is infinite, right? If you add up all of these things, the numbers are getting bigger and bigger. So the only reasonable thing to expect the sum to be is infinity. So this is what we would expect. But
I mean, not really.
well, what would you call it then? What would you say it is?
I mean, it doesn't seem like, even if it adds up in infinite times, it doesn't seem like it should be infinity. Because you can't add up to infinity.
So you would prefer to say that the sum...
Look right.
Ah, okay. So you would just say, I mean, you can't. You would say you can't reach infinity. So you would say, it does not exist or something. Is what you would prefer to say?
Sure.
Is that what you? Okay, that's fine. Yeah, I mean, either calling it infinity or saying it doesn't converge to anything, I think is reasonable. But in string theory, there's a certain very precise sense in which you can say this sum is equal, in quotes, because I haven't told you what this equals really means. It's equal to minus 1/12. Mic drop. I find this hilarious when you tell people this. Like, yes, if you add up all the positive integers, I'm going to declare that sum to be minus 1/12. And if people are outraged. They're like, how can you add up infinitely many positive numbers and get a negative number? That's absolute nonsense. And they're right, it is absolute nonsense the way I've written it, because I haven't told you what I mean by equals here. But in string theory, there's a certain sense in which you could say, yeah, of course this thing just gets bigger and bigger, because you keep adding larger and larger numbers, so it doesn't really go anywhere. But in a certain very precise sense, you can peel off the infinity and see what's left under it. Like, you can see we call it the sub-leading term after the infinity has been removed. And as it turns out, when you remove the infinity, the thing left is minus 1/12, which is actually very important. This number 12 pops up in many places in string theory. So,
but isn't infinity minus 1 still infinity?
Yeah, you have to be careful. When I say peel off, I don't just mean, taking the sum minus infinity or something, because we haven't really defined what it means to add or subtract infinity. You would think a reasonable definition would be infinity minus 1 is still infinity, and you can define it that way. So you have to be a little more careful. And when I say peel off, I mean something slightly different, which has to do with something called regularization, which is not simply subtracting infinity, but it's I don't know how to explain it. It's a more involved process. But anyway, this is what did you say?
The more you know.
Mm-hmm. That was a long tangent, but yes. So if you have the stamina to make it to chapter 7, we will prove the first of those things, maybe the second. All right, one more fairly obvious theorem is that since multiplication is distributive over addition, since you can distribute constant times a sum, you might think that if you have a sum of some expressions that are a constant c, so c is some real number, and x sub I again are expressions depending on the index, you might think if I add up c times x sub I, then that should be the same as first adding up all the x sub I and then multiplying that result by c. And of course that's still true. So the proof is obvious. Since we have this distributive law that multiplication distributes over addition, so you can simply factor out that common factor of c when you write out the definition. So here's the definition of the left side. That's the definition. C times the lower x evaluated at the lower index of summation, so c x sub n plus c x sub n minus 1 all the way up to c x sub m. And by the distributive property, this is c times the sum of each of those terms with the c factored out. But then this thing is the definition of, the sum of x sub I from n to m. So again, for a finite sum, you can simply pull out a factor c. And this is something you'll use occasionally in proofs. Okay, yeah, not super complicated, but thoughts or questions on this?
I do not have any thoughts or questions.
Okay, let's do some actual calculus then with this. So So I hand you a bunch of constants. These are just numbers that don't depend on x. They could be, I don't know, 5 or 11 or something. So if you have a bunch of constants, and then I take this polynomial. So this is just a polynomial from I equals 0 to capital N, a sub n x to the n. So just to be very clear what I mean, I'm going to write out the definition for you. So, oh fuck, I wrote I. Sorry, that's a typo. Obviously the index in this expression is not I, but it's lowercase n. Sorry. So this should be the sum from n, lowercase n equals 0 to capital N, of a lowercase n x lowercase n. What does that mean? Well, when you plug in n equals 0, that's a0 times x to the 0, which is 1, plus a1 x to the 1, plus a2 x squared, plus dot dot dot, plus a capital N x capital N. So this is just a polynomial, a bunch of powers of x with various coefficients. Then I ask you, what is the derivative of this thing?
So we can split this into a whole load of derivatives. Split this into a whole load of derivatives. So we see that a sub 0. Wait, we have a sub 0 there?
Yeah, so that's when the lower index is 0. We have a sub 0 x to the 0. So that's the first term.
Is a sub 0 a constant?
Yep. Oh, fuck. Man, another typo. Sorry. A sub 0. I started a sub 1 here. Yeah, a sub 0 is also a constant. Sorry.
Just check.
Sloppy.
So, I guess we can just go through each and see that the derivative of a sub 0 is going to be 0 since it is a constant. The derivative of a sub 1 of x is going to be 1 because it is, well, just to the power of 1.
1 times a sub 1, though, right?
Ah, right.
Linearity. This is just a line with slope a1, so the derivative should be a. Good. This guy.
It's going to be plus a sub 2 times 2 times x.
Yeah, so 2a2x, and then blah blah blah. What's the top guy?
It's going to be a sub capital N times capital N times x to the power of capital N minus 1.
Good. Okay. So, as we see, this sum, which we got from expanding out the top sum and differentiating each piece, actually matches what we would have gotten from taking the sum originally and just taking the derivative of this thing circled in pink. Right, so if I just looked at the general term a sub n, lowercase n, x to the power n, and I just took the derivative of this guy directly, then we see we get something which would have matched precisely, because I would have said, well, for any lowercase n, the derivative of this guy by the power rule is lowercase n, a sub n, x to the power of lowercase n minus 1, and I still have the same bounds from n equals 0 to capital N. Why is this the same thing? Well, because the first term, when I plug in lowercase n equals 0, I get 0, because here's a lowercase n, so when I plug in 0, that's 0 times this chunk, which is just 0. So that gives me the first term. When I plug in lowercase n equals 1, I get 1a1 x to the 0, which is this guy. When I plug in lowercase n equals 2, I get 2a2 x to the 2 minus 1, which is this guy, and so on, up to capital N. So now we see, since the derivative is linear, and as we've kind of alluded to in the previous couple of slides, whenever something is linear and you apply it to a sum like this, it's the same as just applying the operation to the expression under the sigma and leaving the sigma alone. Whenever you're differentiating a sum, you can just differentiate this guy inside the sum and leave the bounds unchanged. That's the punchline of this. Thoughts on this?
Cool.
No thoughts?
No thought, that's cool.
Okay, good. Very useful. Yes, so here's the same thing said again. F prime, which is ddx, This is perhaps this is why I like Leibniz notation for writing this, because we can see it's again just like a matrix. Like we saw before, a matrix is linear, so m times au1 plus bu2 is the same as taking the matrix and applying it to the vector u1 and then taking it times u2. So you just, if there's a sum, you can just move the ddx into the sum, so to speak, by linearity. So as we saw on the previous slide, that's this thing. Notice that you can, if you prefer, you can now rewrite the sum with different bounds, because when you plug in lowercase n equals 0, as we saw, that gives you 0 times some junk, which is just 0. And since adding 0 does not change the result of the sum, you can drop that term and just start adding at 1, because the only term you're missing is 0, so it doesn't change the answer. So sometimes it's convenient to do this. You just change the bounds of summation if the terms that you drop are just 0, since then there's fewer things to add up. But anyway, either of them is, of course, correct, so that's fine. All right, next thing. Okay, so this is kind of a preview of what we would do in Chapter 7. And you may remember this was actually way back in the pre-test. There was a pre-test question that asked you to evaluate a geometric series. We didn't actually talk about it. I wrote a solution for it and posted it, but I don't know if you read the solutions carefully. So let's see. We're not going to do anything rigorous. We're not going to prove that this sum exists. We're just going to fly by the seat of our pants and say, if this thing makes any sense, what does it have to be equal to? So I'll start things off for you with a hint. So the hint is to assign this expression to a variable x. So let's define a variable x, which is equal to the thing which we're trying to calculate, and see if we can get an equation that relates x to itself, because we know how to solve equations because we're very good at algebra. So if you do that, simply writing this out by plugging in each of the values for the index, well, 1/3 to the power 0 is 1, 1/3 to the power 1 is 1/3, 1/3 to the power 2 is 1/9, plus 1/27 plus 1/81, and apparently we're supposed to keep adding forever, add up infinitely many of these. Okay, so now I'll ask you for ideas. Do you see a way to manipulate the right side of this equation so that it becomes an expression which involves x? In other words, do you see a way to re-express the right side of this equation, or part of it at least, in terms of x itself?
I'm literally just throwing in ideas. Okay. Do we take the derivative of both sides?
With respect to what?
That 1 equals 0. Never mind.
Yeah, if you differentiate this, you're going to get 0. So this is actually purely an algebra question at the moment, sadly. Do you see any common factors? Can you pull out a common factor of some number on part of the right side?
Could we multiply the entire thing by 3?
Yeah, okay. So let's do that. The left side becomes 3x. The right side becomes 3 plus 1 plus 1/3 from 3 times 1/9, right? And then 3 times 1/27 is 1/9. And 3 times 181 is 127, plus ... Very good. Now what do you see? Remember, we're trying to get an equation that relates x to itself. So do you see a way to take the right side of this equation and express it in terms of x using the definition?
I apologize for the pause. I just got my milkshake because of reason.
Is it chocolate again?
Yes.
Aha.
Deep thinking. So multiplying by 3 again isn't going to have us make any progress. Oh wait, could we divide by 3? No, wait, I almost said the thing. Divide by 3 on both sides. Why?
No, we don't need to. Don't need to multiply by anything. That was the key step actually. So we're almost there. This equation is precisely what we want. We just want to re-express it in a way that gives us an equation for x. So, do you see a way? Do you see a part of the right side which can be replaced by x?
Could we replace the No, that doesn't make sense.
What were you gonna say?
Could we set x? I think it makes sense that we. Oh wait, we already decided that. Never mind.
Let's see. We defined x to be this stuff, right? So this x is this infinite sum, and it seems like the right side of this equation is 3 plus exactly what x is, right?
Oh.
See what I'm saying?
That's nice.
They just
so we could divide by x on both sides.
Well, I don't think we want to divide by x. I think we just want to say that this is, let's see, the left side is 3x equals 3 plus x, right? All we're doing is taking this infinite set of terms, which by definition is the same as x, right? That's what we defined x to be. So we're just replacing this part of the equation by x itself, right? That's the key step. Does it make sense why we can do that?
Yeah, I think that's what I was trying to say, and then I realized it made no sense, but then it actually did make sense.
Yeah, I'm being a little sketchy. So you could ask why are we allowed to do that? Because, are these terms really the same? I mean, we kind of multiplied by 3, so in some sense we've shifted the sum so that we're kind of starting later. Does this really make sense? Yeah, I mean, we're going to ignore those for now. We'll prove that this makes sense eventually. But for now, let's just be fast and loose and say, yeah, this stuff is x, so, let's assume this makes sense. And then, well, now you see it's pretty clear. Just subtract x from both sides. 2x equals 3, which means x is supposed to be 3 halves. So I'll put an exclamation point. So this is kind of strange. This seems to suggest you can add up infinitely many numbers. Admittedly, the numbers are getting smaller and smaller, so as we go further out in the sum, they change the result less and less because we're adding smaller numbers. And in a certain sense, algebra seems to be telling us that that sum of infinitely many numbers should be exactly equal to 3 halves. So I think we'll need a bit more theory and proving that this operation makes sense in Chapter 7. But as we'll see, this operation is actually justified. And in fact, you could be a little more general. I'll just tell you that if you're adding up any power of some number which is less than 1, so r to the n, so it's important that it's, r is less than 1 in absolute value, for instance, like 1/3, because that means when you multiply more and more of them together, they're getting smaller. But indeed, it's true that if you add up infinitely many numbers like this, which I remind you is 1 plus r squared plus ... which is the same as 1 plus r times the quantity 1 plus r squared plus ... that you can play this game and say, well, this thing is x, and apparently x is the same as 1 plus r times x. So that gives us an equation which seems to suggest, moving Rx to the left side, x times the quantity 1 minus r equals 1, and therefore this infinite sum is apparently 1 over 1 minus r. So you see that gives us the same answer when r equals 1/3. We get the answer we found a moment ago, 1 over 1 minus 1/3, which is 1 over 2/3, which is 3/2. That's the answer we found. So this seems magical at this point, because this step was very mysterious, but, you know, it can be made rigorous. Okay, thoughts on this?
I do not have any thoughts.
Cool. Yeah, here's the same thing. Add up all of these powers of 1/3, factor out the 1/3. You can either multiply both sides by 3 or factor out the 1/3. You get the same answer. And when you solve for x, we found that this sum equals, I put equals in quotes, because we don't really know what this means. It's a little sketchy, but it supposedly equals 3/2. Good. All right. Let me say one more thing, since this, I think, is also useful in writing some expressions. We've seen in the previous slides a way to very compactly write down a sum of many terms, x1 plus x2 plus dot 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 plus x sub n. We say, all right, that's going to be this thing. It's going to be the sum from I equals 1 to n of x sub I. What happens if you're going to multiply a bunch of factors, I guess? So if you're multiplying rather than adding x sub 1 up to x sub n, there's a totally analogous notation which is called product notation or pi notations. This is a capital Greek letter pi. You do this in LaTeX with /prod, I think. Is it prod or product? I think it's /prod. It's a Greek capital letter pi. So it works just like the capital sigma. You write the product from I equals 1 up to n of x sub I, which just means x1 times x2. Ah, good, you're checking for me, thank you. Did it actually work?
It doesn't work.
Oh, so it is /product, my mistake. Oh wait, did you do the wrong slash?
I did.
Yeah, it is actually prod, you just need the right direction.
Lovely.
Whoops. You need Kieran's orientation changing staff to change the orientation of your forward slash. Okay, so same thing. Let's see an example where we use this. So this is the slide I alluded to, which I've included to make the joke. But we saw before that the logarithm of a product of two numbers, log of x times y, by this rule that we proved, is the same as the sum of the logs, log of x plus log of y. And by straightforward generalization, if you have log of a bunch of numbers multiplied together, a1 times a2 times dot 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 up to, I forgot the dot 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 here, but times dot 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 up to a sub n, that's the same as the sum of the logs of each of those numbers. So as an example of how to express an equation in sum and product notation, you could write this by saying the log of the product from lowercase n equals 1 up to capital N of a sub n, which is this thing, is the same as the sum of the logs. So the sum of the logs from, again, n equals 1 to capital N of log a sub n. So, well, or u, I guess. This is the joke I wish to include. But the thing to note is that on the left side, the product appears inside the argument of the log, right? Because this is a single logarithm of a product of numbers. On the right side, the sum appears outside the log because we are adding up logarithms. It's not the logarithm of a sum. It is the sum of the logarithms. So, anyway, hopefully this shows an example of why this notation is very powerful, because now we can express this thing in this much more compact notation. Thoughts on this?
I have no questions or thoughts. I don't have any comments to make outside of the fact that this is really cool. I need to come up with a better comment.
Yeah, it's not super deep, but yeah, if you have even, just passing thoughts that do not seem especially contentful, I'm still happy to hear them. Okay. Alright, so can we do a similar thing with exponentials, right? So we saw that the exponential of a sum is the product of the exponents. So this is kind of the opposite of the log rule. If you take e to the power of a sum, it's the product of each of those powers. So I'll ask you, can you write an expression that involves both the capital sigma and the capital pi that generalizes this rule to an arbitrary sum of numbers? So in other words, I'm asking you to write a product and sum notation expression that tells me something about this thing, e to the power of that sum. What should I write?
All right, we are going to write down that. Well, let's see. Oh, yeah, this is cool. So we're going to have e to the power of the sum. Below we have n equals 1. Trying to remember all the things is hard. On top we have, I guess, capital N, right. Sorry.
Good.
And to the right we are going to have a sub lower n.
Good. Okay. And what should this be?
This is all equal to the product of, let me think. So is product, I'm trying to remember, is product notation in the same form? Just, well, I mean same places?
Yeah, use the same index, lower and upper, and use the same convention that you start from the lower one and multiply up to the higher one. Yeah.
Okay. So below it we have lower n equals 1, and above we have capital N of e to the power lower n.
A lower n, yeah. Good.
Okay, yeah, makes sense.
Yeah, good. So this is the generalization of exponent of a sum, or exponential of a sum, that, again, in a certain sense, the exponential is special because it converts sums into products, right? If you take the exponential of a sum, it's the product of the exponentials. The log does the opposite. The log of a product is the sum of the logs. So this is another way of saying that exponentials and logs are inverse functions because they have opposite effects of converting sums into products versus products into sums. Cool. Questions here?
I have no questions.
Alright, I think that's the last. Yeah, well, this is the same thing we just... one thing I wanted to say, though, is occasionally it's a pain in the ass if you have e to the power of some huge expression, right? Because, I mean, usually you put small things in the exponent because they're supposed to be raised on the page. So a common way to get around this is if you're going to write e to the power of some giant expression, we write e in a different way. You use exp, which is short for the exponential function, instead of e to the power of junk. So it means the same thing. This is exactly the same. If you write exp with parentheses of, say sum n equals 1 to capital N of a sub n, it means the same thing. It just means e to the power of this junk. But it's easier if you're writing something huge to not have to put this in a subscript. You just put it in the parentheses of some argument. It's just like writing, sign of stuff, right? You just use this because it gives you more space. Yeah. Not a very important comment. Just want, in case you are confused by this, I want to flag that piece of notation. All right. And my new roommate just texted me asking what the address of the apartment is. I should let him... fucking my phone shut off. Alright, I'm not going to respond to him then.
Nice.
I've been having problems with my phone that it just shuts off randomly. Well, while it restarts, I will give you some time to think about these multiple choice blitz questions. So these are just stolen from various standardized tests, which are perhaps not the most inspiring, but,
Lovely.
Yes, you remember this one from Slack. I actually think this is kind of cute. Okay, so what should we do? F of x, I will give you a hint to start, and then maybe you can think about it for a minute or so. But the hint is to write this first, since e to the x is in the downstairs, we can write this as e to the minus x times the quantity x minus 1. And then the hint for, you don't actually need to take 19 derivatives by hand. The hint is write down the first few derivatives, f prime of x, f double prime of x, maybe if you need, go to number 3, and then the pattern will become very clear. And then you can kind of just guess what it's going to be at the 19th one. So whenever you're ready, you can either tell me and I'll write them up here as you compute each one, or if you want, you can do it on paper, whatever you like.
So I actually can't remember what the derivative of e to the negative x is. Proved it.
Well, you could just chain rule, right? We know d dx of e to the minus x. This is a composite of functions. The outer function is e to the x. The inner function is minus x, right? That makes sense.
Yes.
Yeah, if you prefer, just think of this as minus 1 times x. Yeah, good.
Cool.
Okay.
So for our first derivative, we have in deep thinking. Okay. Wait, why am I having... I'm still...
Let's see, we're product ruling, right? So...
Yeah.
Good.
So we have negative e to the negative x. That's right.
And then times the second one left alone.
Times... Yeah, x minus 1.
Good. And what's the second term?
Power of negative x times... it's just going to be nothing, so it's 0.
Or, well, the derivative of this thing is 1, right?
Oh. I thought that the 1 would cancel out. I don't know what I'm talking about. I mean 0 out. I don't know what I'm thinking.
Yeah, careful. So the derivative of x
Anyways.
is 1. The derivative of 1 is 0. So this is 1 minus 0 is 1, right?
So this is going to be e to the power of negative x.
Good, okay. And I will insert one more simplification because it'll make it easier to see the pattern. But notice that this is a common factor. I mean, I'm not going to write, well, maybe I should write it out. So this is minus e to the minus x times x. And then if you factored this, or distributed, I guess, to multiply this on the inside, this is minus e to the minus x times minus 1, which is plus e to the minus x. And then we have another plus e to the minus x. So the point is that if you combine the like terms, this is, you know, these two conspire to make a 2e to the minus x. So this is e to the minus x, or I guess if you prefer, you can write the minus sign. Yeah, no, I'm not going to do that. E to the minus x times 2 minus x, right? So here's the 2, here's the minus x. So I'll just write that small down here. This is just algebra. E to the minus x times 2 minus x. Okay, now what's the second derivative?
So we are going to have negative e to the power of negative x times 2 minus x? Yeah, that's right.
Good.
All times e to the negative x times...
That's a plus, right? Not a times. Product rule.
Right.
Good. E to the minus x times, what was it again?
Times 1. Excuse me, negative 1.
Good. Times minus 1. Okay. And now you can kind of see again, this is minus e to the minus x times 2 minus x, and here's a minus e to the minus x. So if we move that into this this product here, if we kind of, what's the word for that? Not distribute, factor. Yeah, factor the minus e to the minus x. This is the same as minus e to the minus x times 3 minus x.
I do not entirely understand that step.
Okay, good. Let me do that more slowly. So I'll go up here.
I saw you did it last time, but I didn't understand it there either.
Ah, okay. So I'll just write out the 3 terms. So first I distribute this guy. So minus e to the minus x times 2 is minus, blue's probably not good to write there, pink. So multiply this by 2, minus 2 e to the minus x. Multiply this by the minus x, minus minus is a plus, e to the minus x times x is plus x e to the minus x. And then this term is left over, minus e to the minus x. Now we see that the first term and the third term are the same. We can combine the like terms. Minus 2 e to the minus x minus 1 e to the minus x is minus 3 e to the minus x. Right? So combine those, and you get minus 3 e to the minus x plus x e to the minus x. And now you factor out the e to the minus x. Right? So this is e to the minus x times minus 3 plus x, or if you prefer, x minus 3. Sorry, we're getting a little crowded here. Okay. Are those steps satisfactory?
Yes.
Okay. Then let me erase it to make more room. So, this should be, as we said, this should be equals. So now two things changed from the previous thing, right? Now there's a minus sign outside, so it's now equals minus e to the minus x times, and the 2 has changed now to a 3, right? So I think it was 3 minus x. So we're starting to see the pattern that on the one hand, the thing inside the parentheses is increasing by 1 each time, 2 up to 3. We should take one more derivative to check, but then also the sign outside is flipping, right? It was positive here, and it's negative here. So we would guess, here's my guess for the third derivative. My guess would be, well, the sign outside should flip again, so it should go from a minus to a positive, e to the minus x, and the 3 should go up to a 4 minus x. So that's my guess, but let's take the derivative by hand and see if it matches. Okay, so this is getting very sloppy, so I'm just going to erase this and give us more space to write the third derivative. Okay, so let's just use the product rule. What is the f triple prime of x using this expression?
It's going to be e to the negative x times, keep thinking, I mean just 4 minus x, but we didn't really calculate it, sure.
Well, we're product ruling this thing, right? So it should be e to the minus x times 3 minus
right.
x.
I don't know what I'm saying. Yeah, 3 minus x plus e to the negative e to the power of negative x times 1. Negative 1.
Good. Negative 1. Okay, so now let's simplify that a little bit, because that's, yeah, I really should have given myself more room. So I'm going to start erasing the upper derivatives, or at least the original function. Okay, so let's simplify this. This thing is, I'll do out the algebra again. So when I distribute this, this is 3e to the minus x, and then minus x e to the minus x. And then from the second line, minus minus makes a plus, so that's plus e to the minus x. And now we see the first term is a 3, the last term is a 1, so that's the same as 4e to the minus x minus x e to the minus x. So overall, when we pull out the e to the minus x, it's e to the minus x times 4 minus x. And indeed, this was our guess. It matches our guess. So now we can kind of guess the pattern. I've run out of space, but I'm just going to erase this stuff and rewrite it. Let's see, just so I don't forget the first one. F prime is e to the minus x, 2 minus x. Okay, so let's guess the pattern from the first 3 calculations that we just did. Man, this is pain. See, I could have just erased the whole screen if I didn't want to keep that. Okay, so the first derivative was f. I'll write it as 1 so we can see the pattern more easily. Was e to the minus x, 2 minus x. And then the second derivative that we computed a moment ago was f2 was minus e to the minus x, 3 minus x. The third derivative was back to a plus e to the minus x times 4 minus x. So you can kind of see the fourth derivative is probably going to be back to a minus e to the minus x times 5 minus x. And now here's the way that you would write the general term in this pattern, right? How do you tell the reader that the signs change? The sign is supposed to be positive if the number is odd, and negative if the number is even. Well, the way you do that is write minus 1 to the power k plus 1. Why does that work? Because if k is odd, like 1, odd plus odd is even, and negative 1 to an even power is plus 1. If k is even, like 2, say 2 plus 1 equals 3, negative 1 to the power 3 is a minus 1. So this factor gives us the overall sign flipping behavior. Then we write e to the minus x. And then what should I put inside here? Well, it looks like each time the constant inside the parentheses is the order of the derivative plus 1, right? 1 up here, 2 over here, 2 here, 3 here, and so forth. So I should probably write this k plus 1 minus x. So this is our guess for the general term in this series of derivatives. Okay, so does this expression that I just wrote, that was a little fast, and I don't know if you've seen this trick before of expressing sign flipping like that, but are you happy with that general expression, or are there questions?
I'm happy with that.
Okay, so now that we've gotten this far, now we can answer the question, what do you think the 19th derivative should be? Which of these choices?
It should be C.
Good. Yeah, it was kind of a grind, but I mean, it's a slightly fun as far as standardized test problems go, that's not the worst. Okay. Thoughts on this problem?
I have no thoughts.
Onward. Okay, so let's make sure that that was actually right. Yeah, it looks like the same thing. I wrote it slightly differently here with x minus instead of the other way, but the punchline is that each time you differentiate, product rule and combine like terms to get either an overall minus or an overall plus times e to the power minus x times an expression involving x minus a constant. The thing I wrote on the previous slide is the same as this. I just wrote, I distributed the minus and flipped the order of the two guys inside, so it's the same thing. But either way, then you guess the pattern, your sign has to flip every time, and you need this constant inside to increase. And that gives us the correct answer, which was C. Okay, here's another guess the pattern style problem. So f is a function having derivatives of all orders, so using our notation for this, we'd say f is c infinity, right? Remember, c3 means it has 3 derivatives. Here you're saying you have infinitely many derivatives. So if f is c infinity, and f prime equals f squared, right? So you take the derivative, you get back the original function squared. We're going to try to guess a pattern to find the nth derivative of f at x. So I'll do this over here again. I think we won't need as much space. So I'll do the same thing where I write derivatives with a number in parentheses. So we know the first derivative already. That's f of x quantity squared. Alright, so now I'll ask you, if I differentiate both sides of this equation with respect to x, on the left side I get f2 of x, on the right side I use the chain rule, so what do I get when I take the derivative of the right side?
We have for an outside function x to the power of 2, and our inside function is f of x, so we are going to have thinking is going to be 2 times f of x times f of x squared.
Yeah, you skipped a step, right? The inside is f prime, and then you plugged in f prime as f squared. Is that how you did that?
Correct.
Okay, good. That was fast. Very nice. Yeah, so good. So that's 2 times f of x cubed. All right, let's do another. Take another derivative. What do we get when we differentiate this guy?
So once again by the chain rule. Let's see. This is going to be 2 times whatever we're going to get by the chain rule. So x to the power 3 for an outer function and f of x for an inner. Still thinking. 2 times 3 f of x squared times f of x quantity squared.
Yeah. So again, we're seeing this thing happen again every time we chain rule and multiply by the derivative of the inside function. The derivative of the inside function is always going to be f squared. So we pick up every time we remove one power by the product rule, or sorry, the power rule. Every time we remove one power, but then add 2 powers back. So now we're starting to see why the power is going up by 1 every time. So just combining them, this will be 6 times f of x to the power 4. So now we see, it started to the second power. When you differentiate, you lose 1 from the product rule, but you gain 2 from multiplying by the chain rule. Then you do it again. 3 goes down to 2, but then you add 2 back, so it gets up to 4. I'll just do the next one for you. f4 is going to be the same thing. You pull down a 4. 6 times 4 is 24. F of x cubed times derivative of the inside function is f of x squared, and f cubed times f squared is f to the 5th. So f of x to the power 5. Alright, so now can you guess the pattern? The nth derivative, can you guess the pattern from the first 4 data points, what it's going to be?
I'm inclined to believe that it is b.
B, yeah. Looks right. N factorial f of x to the power n plus 1. And indeed that's correct. So why is that correct? Well, the factorial is because you multiply by every number as you differentiate up, because first you multiply by 2, then you multiply by 3, then you multiply by 4, then you multiply by 5. So this is building up the factorial from the bottom. That's where the factorial comes from. The n plus 1 comes from starting with 2 and then each time adding 1. Right, so it's going to be n plus 1 in the exponent. And indeed that's the right answer. So yeah, I think here I just went up to f3, but as you said, when you differentiate, you start from f squared, then you get 2f cubed, 6f to the 4th, and in general n factorial f to the n plus 1. So yeah, it's kind of cute, again, as far as standardized test problems go. Thoughts or questions here?
I have no thoughts or questions.
Alright, let's do a slightly less computational one. So this is our favorite trick again of defining these functions that do one thing on the rationals and another thing on the irrationals. So let's just draw this to get some idea of what this thing looks like. So I'll use the trick of dotted lines. So on the rationals, this thing is an upward sloping parabola 3x squared. So it looks something like this. So I tried to make these dotted but didn't work very well. So this is on Q. Now, if it's an irrational number, which I'll do in a slightly different color, this is supposed to be minus 5x squared. So this is a downward sloping and steeper parabola, but still a parabola. So this is, I don't know how to write this, not Q. So these are the two, I mean, the way I've drawn this makes it look like this fails the vertical line test, because it seems like it touches 2 points, but hopefully you get that what I'm trying to say. It doesn't actually fail the vertical line test, because at every point it's either one or the other. It's the top if it's rational, it's the bottom if it's irrational. Okay, so now here's the question. Which of the following is true? Is f either discontinuous everywhere? Is it continuous at 0 and differentiable at 0? Is it continuous at 0 and not differentiable anywhere? Or is it continuous at rational points and not differentiable everywhere? Or is it continuous at irrational points and not differentiable anywhere? So basically all we have to do is decide where is it continuous and where is it differentiable, and then we'll know which of these choices it is. Okay, so what do you think about first continuity? Where, if anywhere, is this function continuous?
I believe that it is only continuous at 0.
Good, yeah. So the picture makes it kind of clear because this is the only point where the two touch. And you could prove this if you want pretty easily, right? You just let epsilon greater than 0 be given. This guy's continuous, so find a delta for this guy. This guy's continuous, so find a second delta, say delta 2 for that guy. Just take the min of the two deltas, and as you can see, it gets very close to 0. Good, so I agree. It's continuous at 0, so that rules out this and this and this. We're down to B or C. Okay, so now the harder problem is where do you think it's differentiable?
It would seem that on just one side it has two potential slopes, but I don't know how to prove it.
On one side, by side you mean the top or the bottom?
Oh, wait. Yeah, by side I mean left and right, but by the two potential slopes I'm talking about the two parabolas.
Oh, I see, yeah. So at most points I agree. There's two, well, I can't go that far. But let's look at this point, for instance. Does it have a well-defined derivative here? Well, no, because as you say, there's two potential slopes. There's a downward slope on the rationals, and there's a very steep upward slope on the irrationals. So here the derivative does not exist, because it's going to oscillate between these two very different slopes. So at most points it's not differentiable. Can you see any point where the two slopes are actually the same?
At 0.
Aha, good. So at 0, the slopes are both 0 horizontal lines. So indeed, choice B, it is differentiable at 0 and continuous at 0, but not continuous or differentiable anywhere else. Of course, we could prove it, but we don't have to because it's a multiple choice question, so once you decide what the answer is, you're done. Okay. Thoughts on this?
I have no thoughts.
Sweet. All right. So I will say that again, but it's effectively what you just said. It's continuous at 0. Do the same thing. You could prove this if you wanted. It's differentiable at 0, which you can just kind of tell intuitively from the picture, or you could prove it with epsilon delta using the difference quotients, but for a multiple choice question we don't have to do that, so we can be lazy. Okay, so this question is a little trickier. We define a function g of x, so this is g of x, it's e to the power 2x plus 1. So just for example, g of 0 is e to the 2 times 0 plus 1, which is e, so that will be useful. And then we're given this limit. The limit as x goes to 0 of g of x minus g of e all over x. And we're asked to compute what that limit is. Now, initially it seems like this is a very hard problem because you would think, well, I have to plug in g of x, and that's going to be something complicated, and then I have to figure out what g of e is, which is e to the 2e plus 1, and I don't know what that limit's going to be. It seems like it's very complicated. But I'll give you the hint that this limit written here is secretly the definition of a particular derivative. So this is the definition of a derivative of a certain function involving g. It's not g itself, but it's going to be a derivative of actually g composed with g, or g of x, at a particular point.
I'm getting deja vu here. Why am I getting deja vu? Help.
Have we done this problem before?
I don't think we have, but something feels weird.
I guess deja vu is better than when you had that like random sadness come over you like 10 meetings ago.
Weird still. Okay, I apologize for interrupting.
No, I like interruptions. More interruptions is much better. Okay, so anyway, so my challenge to you is first, can you see what derivative this difference quotient is defining? And once we've figured out what derivative it is, can we apply our derivative rules to find out what the numerical value of it should be? So first, can you see what derivative this is defining?
What is e?
E is the base of e to the x, right? So like e is, we defined it in the stupid way last time, n goes to infinity, 1 plus 1 over n to the n, this guy, that thing.
Yeah, I forgot that I thought e was a variable for a second. I mean, it is.
Oh, it's a constant, but yeah.
Yeah.
So the hint is that e is the same as g of 0. Maybe I'll rewrite it. So x is a dummy variable. I'm going to replace x by h, since I think this might jog your memory. I'm going to replace x by h, and then I'm going to do this. G of g, so this should be h, but h is the same as 0 plus h, because I can always add 0 to anything. So far I haven't done anything. I've just changed the name of x to h and added 0. Then, as I've told you, e is g of 0, so I'm just going to rewrite e as g of 0. G of 0. And then this is all over what was called x, which is now called h. So maybe that will jog your memory. Can you see what derivative this is?
This is... Wait, is this the, thinking? Would this be the second derivative of something?
It's the first derivative,
Something
right? Because it's just one... none of these are primes, right? The second derivative would be the limit as h goes to 0 of g prime of something, right?
Okay. I don't recognize this, but I'll keep thinking.
Okay, yeah. Take a few more seconds. Maybe it would help if I define a new function. So to aid you in your quest, if we define a new function f of x, which is just going to be the composite g of x. I don't know if that helps. Well, maybe I'll just ask you. So if I rewrite this line in terms of f, so everywhere you see g of something, just replace it by f of something. What should I write on this line?
We will have f of 0 plus h minus f of 0 all over h.
Good. What derivative does this define?
That defines the derivative of f at 0.
Good. F prime of 0. But what's f prime in terms of g using the chain rule? So if I differentiated f, what would I get?
Sorry, say that again?
So if we just look at the top equation, f of x is g of x. If I differentiate both sides of this, because I want to find f prime, right? So differentiate both sides of this equation with respect to x. On the left, I get f prime of x. What do I get on the right?
By the chain rule, we have that g prime of g of x times g of x.
Yeah. Or wait, g prime of g of x times the derivative of the inside, right?
Oh, okay.
So
Getting it confused. Oh wait, I was getting it confused with product rule.
yeah, product rule is derivative first, second left alone, derivative second, first left alone. But chain rule is derivative of outside with inside left alone times derivative of inside. Right. Okay.
Yeah.
So now we know that we have this dictionary. If you want to evaluate f prime at any point x, you just take g prime of g of that x times g prime of that x. So if I want to write f prime of 0 in terms of g, what do I write?
G prime of g of 0 times g prime of 0.
G prime of g of 0 times g prime of 0. Good. Okay, so we've done all the hard work. We figured out what the mystery limit is. Now we just have to apply our derivative rules to find out what this thing on the right side is. So let's go back over here to our definition of g of x. G of x is e to the 2x plus 1. So I'll write that over here. G of x is e to the 2x plus 1. Now we're going to need g prime apparently, because that appears on the right side. So what's g prime of x?
Okay, I'm just going to put this thought up for... What if we could take the derivative of both sides of our maroon equation there?
This one up here?
Yeah, would that give us any useful info?
So this is evaluated at a particular point. So if we take the derivative with respect to x of this equation, both sides are constants, right? G of 0 is just a number, and e is a number. So we would get 0 equals 0 if we differentiated that.
Whoa.
Magic. It's a good thought, though, yeah. That's a useful hunter's instinct that you're developing, is that whenever you have some equations that are given and you want to extract more data, it's almost always a good idea to take derivatives. It almost always gives you more useful information. But as it turns out in this problem, we don't want to differentiate the maroon equation. We want to differentiate the first pink one here, where there's still an x.
So I'm inclined to believe that we could simply do the... Oh wait, no, we can't do the, trying to remember. We've proven this before. That's the problem. I can't remember where we proved it. How to calculate this. Sure, just, I guess we can do the chain rule.
Yeah, good. So let's chain it. So what do you get?
Outer function is e to the power of x, inner function is 2x plus 1. So we're going to have e to the power of 2x plus 1 times 1? No, excuse me, 2.
2, good. Good, so that's g prime. Okay. So that's all we need to evaluate this guy. So we're trying to evaluate g prime of g of 0 times g prime of 0. We know g of 0 is e, right? So I'm just going to rewrite that. I'm running out of room, but I think we only need one more line. So f prime of 0 is g prime of g of 0. G of 0 is e, so this is g prime of e times g prime of 0. Well, let's look at this equation. What is g prime of 0?
G prime of 0? What did I miss? G prime of 0 is... thinking that is going to be 2e.
2e, good. Alright, so we have g prime of e times 2e. Last step, what is... I'll write another line for us. So what's g prime of e?
It's going to be e to the power of 2e plus 1 times 2.
Good, okay. So now I'm going to do very sloppy board work and erase and start calculating upwards because I've run out of space. So this equation, oh boy, this equation is now going up here. So g prime of e, as you've told me, is e to the 2e plus 1 all times 2, and we have to multiply that by the second factor, which is again a 2e. Maybe it helps to write this as 2e to the power 1. So I think we have one more step. We combine the 2's to a 4, and then multiplying exponentials with the same base. How do I combine these? I claim this is e to something. What is the something?
So I believe that we can add.
Yeah.
I think so. We're going to have 2e plus 2.
Good. 4e to the 2e plus 2. Good. And indeed, that is, well, I've covered it up with my sloppy board work, but that is just e. Capital E. There's too many e's in this problem. E to the 2e plus 1. Okay, so, yeah, I think that's actually a kind of cute problem, but just to recap what we did, because there were a few steps, right? So first we had to recognize that this limit that we were given is secretly a derivative. What derivative? Well, it's the derivative of g composed with g, which means g of x. So first we recognize that. Then we use the chain rule to get the derivative, g of x. Well, we didn't write this out because we evaluated at 0, but when you evaluate at 0, that's the same thing you told me a moment ago, which was e to the 2e plus 1 times 4e, which is the same as 4 times e to the 2e plus 2, which was, confusingly, choice capital E. Good. So this is good because it tests a few different things, definition of derivative and chain rule. But, all right, thoughts on this guy?
I have no thoughts.
All right, last one then. Ooh, too far. I think this one's a little easier, but let's see. So f is a function such that f of x is the same as f of 1 minus x for all real numbers x. And we're told that f is differentiable everywhere, so it's c1. It has one derivative. And then we're asked, what is f prime of 0 in terms of, some other property of f, like f of 0 or f prime of 0. So this time I'll give you no hints and see if you can intuit the direction to go. Where should we start to figure this out?
So I guess we can take the derivative of each side of the function that we're given.
Okay. What do we
do? So f prime of x equals, in parentheses, f of 1 minus x and parentheses prime.
Yeah, so this, and then what else? Chain rule.
You automatically apply the chain rule for me, so that's going to be do -1.
-1. Okay. Now we're asked about f prime of 0, so what do I do now?
So we know that f prime of x equals negative f prime of 1 minus x, so we insert 0 into what we have and see that f prime of 0 equals f prime of 1?
With a negative, yeah.
Negative f prime of 1.
Good. Oh shit, I didn't want that. Alright.
It's e.
Yes, you are correct. I'll just rewrite it quickly for my own benefit. As you said, f prime is minus f prime of 1 minus x, and therefore f prime of 0 is minus f prime of 1, which is choice E. So no magic here, just differentiating both sides, and indeed, when you differentiate both sides, you find that the derivatives are related at these 2 points. Good, okay, so yeah, hopefully these multiple choice questions are not too boring, but I think it's useful, even though they're not as involved as like the meaty daily challenges like doing Schwartzians and stuff. It's sometimes nice to have these kind of quick, crunchy problems just to, build your chops.
Quick note: Schwartz was German.
Ah, good. That makes sense. His name is that the same Schwartz as the Cauchy-Schwarz inequality? I don't know if it's on his Wikipedia page.
I have no idea what you're talking about.
Cauchy-Schwarz. It's probably the same. I don't know. I don't know if it's the same as in the Schwartzian. But anyway, this is a very famous inequality, Cauchy-Schwarz inequality. It's up there with the triangle inequality. Actually, it's probably number 2 after the triangle inequality. If I had to rank inequalities by how often they're used, probably triangle then Cauchy-Schwarz. But
yep, they're the same guy.
Ah, good. I guess there's not that many people with the last name Schwartz, so I should have guessed.